at the time, instead of allocating the new pages to create the process, we can have the pool of the free space only for creating the process, then assign such a pages. Okay, so that is called the copy on write. So we can maintain the pool. Okay, it's a zero field on demand. It can be used for only for creating the processes, so we can reserve the certain number of the pages for the new processes. Okay? If you use such a approach, the copy on write, that is called a weak fork. So probably you have seen the if you check my handout at the beginning of the semester, I hand out the system code, example of the system code. Instead of the fork, the system code, they use the weak fork. Weak fork means the virtual memory fork based on copy on write. They reserve the certain space, virtual space, for the new process. That is a weak fork. So most of the current operating system core, they use the weak fork instead of the traditional fork EXE.
So they're just sharing the same memory, that's what it says, copy on write.
Oh yes. So for example, this one is a process 1 and process 2. If the process 1 create the process 2, they are sharing such a page, and just in case they need to change what the EXEC, they just a copy, and that time the page is reserved. You can get the new page from the pool of the free pages. That's the copy on write. What happened? No free frame. That's the problem, right?
We can't start with extend the memory.
We cannot extend the physical memory, right?
Virtual.
Even though we extend the virtual memory, that doesn't mean the CPU can read the data from the virtual memory. Virtual memory space is actually swap space, but based on the pages. Okay, not entire memory, not entire process. So it's still in the hard disk drive, secondary storage, which means CPU processor cannot access. So, what if no free frame? We need to page out and bring new pages. That's the only solution. So page in and out. Okay. The problem is each page will be victim. Each page will be the page out. Any solution? Any idea? First come, first out. So all this one will be victim. That makes sense. Oh really? That makes sense. If the page was in the first time, which means higher chance never been used. Okay, I'm not sure, but that makes sense. Also, latest one, because it's late, the listened one, is there any higher chance to be reused? So that is the idea to decide the victim. That is the main role of the pager, to decide the victim page. Okay, so in case anyway replace the pages, if that is the changed pages, that is called the dirty pages. This is a very important issue in the database, like to keep the consistency of the data. However, operating system is not very critical if the one of the page is changed, whether the other process read, whether we can change it, or dirty data is the page out. Okay, so we are not going to be very serious to deal with such a dirty page or the modified page, but this is a big issue in the database. Why? Yeah, for example, think about, so this page, this block has the interesting rate, like the 1.0. Why this one is read by the process, new customer, new account. Then what if we change the value, interest rate 1 point to the 10 point? So what about this one, the new? So can we guarantee the 1 point or the new one? So it's not consistent. So database is a very critical such a consistency, but operating system is relatively general, such a 30 pages. So at the time we can mark as it's a 30, and sometimes it's not needed, then page out. Okay, so
if we page out, where does it go?
page out going to the virtual memory space, but it cannot be accessed by the CPU processor. Okay, so that is a virtual memory. So this slide shows how it works. So for each process, so we have the two process. This is one and this is a two. Okay, each process has their own. Okay, the page table is a mapping table. So for example, M is the 3 is in the valid. Right now 3 is the M is here the 4, something like that. Okay, so load M, so it's executed, then the load M, the M will be loaded, something like that. And also it's a 1, 0, 1, 2, 3. So this is the page number, logical page number 0, 1, 2, 3. So make sure. So 3 is the here. So this is the H. Okay, 1 is the 4. 4 is the load M. 2 is the 5. 5 is the 3. Then once you execute this one, load M, to load M. So this is invalid, which means this is not loaded yet. So you need to load to here. This one is reserved for the system, operating system. So there is no space. Okay, this is the this require page replacement. We need to determine one of these as the victim page. Okay, then what about this one? What is this? This is a virtual memory. Okay, still it's in the hard disk drive. That's the one thing. Many of the students are confused. So this is the hard disk drive. Even though name is a virtual memory space, it's a logical extension of the memory space, but it's the full swap space in the hard disk drive. So we need to find for the CPU to access such a page, and we need to load into the physical memory. So that is called the page replacement. Also, this kind of situation is called page fault, because we cannot find the M to load into the CPU register. We cannot find it. So that is called page fault. Page fault is the thread, so usually called the thread, not interrupt. So it's the cause something extra action. That is a page replacement. So problem: how can we determine the page frame? Here, victim page. Yes.
So every time CPU wants the access to the pages, does it straight refer to the main memory, or it first checks with the
first check the page table, okay?
Right.
Then the page table, so from the memory, from the CPU knows the relative address, offset address, okay? For each process. Then using the processor, the mapping table, okay? Memory mapping table, you can find the physical memory page frame. Okay. At that time, in case this frame is invalid, which means you cannot access from the physical memory, then that causes a page fault thread. So everything stopped. Then CPU at that time context switch and process other process depending on scheduler that you learned before. Then this one pager will get the signal. It's a page fault. Whenever you have the page fault, pager will load this one then CPU can access. However, if this time you cannot find the free space, that require page replacement. Okay, so we are going to see how can we replace the page. In other words, how can you find the victim pages? That is the problem. Okay. So this slide shows how the page replacement is working. So this is a page table, as I mentioned. In case the F is okay because it's valid. What about the 0? This one is not valid. This is called the page fault. So in case of page fault, we need to load this page. However, if we cannot find any free pages, so we need to decide one of the pages as the victim. Okay, then bring to that page into the victim page space. Okay. So to discuss about such a page replacement algorithm, first I'm going to show the algorithm very quickly. Then we will go back here again. Then we'll discuss detail. First one is first in first out. Old one will be victim. That makes sense. That's one. And second is optimal. Optimal means what is the optimal case to select the victim? If the page is no longer used future, that will be the best one, right? If the page will be used recently, we'd better keep it, right? If we replace the page that will be reused later, we need to page fault again. That is overhead. So we need to find the page which will be used, which will not be used for future. That's optimal. Problem? How can we see the future? That's the reason it's the optimal is to use the for the reference. Okay? And because we cannot predict correctly the future, why don't we take a look at the past? Which one is the recently used one? Okay, so which is called the least recently used algorithm, FRU algorithm. If that one is least recently used algorithm, at least used the pages, which means lower chance to be used, right? Because the one is used here, three is used old, so we can. That LRU algorithm is used for database also, for the buffer management. And there are various versions of LRU algorithms, so we will take a look at. So that is the basic approach, basic algorithm that we are going to discuss. So to do that, how can we represent the pages? So we are going to use the reference string. Each one represents page number as well as the data. Actually, the real page is like the 512 bytes. So each one has a page ID, and each page has something, the instruction and data, but it's more complicated. So why don't we simplify the problem by assigning for each page as the number itself. So number itself is both the indicate the page ID as well as the contents. Okay, so this is called the reference string. So we are going to use the two reference string. Okay, one is 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. That means CPU core first page 1, then next 2, next 3, next 4, then next 1. Page 1, page 2, page 5, and so on. Okay? So
That's
yes.
That's what CPU is requesting. Right?
Yes. So actually, each number indicates a page number as well as the contents inside. Okay? And the second example is a little bit more complicated one, 70120. So we will use this one, same reference string, same pattern of the calling the page from the CPU, then compare the performance for each algorithm. First in, first out, and optimal, and LRU. LRU, the various, the version of the LRU algorithm. Okay, so we are going to use this. So in your project B, you are going to implement this algorithm. So algorithm itself is simple. So input is reference string. Okay, output is how many page fault. Right, page fault will determine the performance. We will see. Okay, usually the more physical memory you have, the better performance. Right, the x-axis indicates the number of frame. Number of frame means it's a physical memory size. And number of page fault is a higher, the worse the performance, right? So this is what we expect. This is general. Is it true? Not always. So we will see such an example later, like that is called belated anomaly. The more number of frames we have sometimes, the less, the more the page fault. Sometimes it happens. So we will see later. But this is what we expect for the performance along the different number of page frames. Yes.
So we can't say that more number of frames or bigger the.
Not most of the time, yes, but sometimes not. That is called the anomalies, the belated anomaly. We will see why that happens. Then once you understand that is the reason sometimes when you are doing the programming, any programming, okay? So for example, one of the typical examples is a for loop. Usually you are using for loop for I and j, okay? Then if you allocate the array, which one is better, I, j or j, I? So I is 1 to 10, j is 1 to 10. Then so it's a for loop. Then we are going to assign array I and j. Or another one is j, I. Both of them are the same, 10 by 10. Which one is better? Have you ever learned in your programming class? Is there anyone who define such a way, j and I, j, I array? Most of the time, I, j. Why? Have you ever thought about it? Why don't you find at home? Which one is better, when, why? Okay? When I learned the programming, C programming, my instructor mentioned this, you need to use such a way. If you understand the process structure, what is the heap, what is the heap, usually it's heap, and then pointer, you can understand. At that time, why we need to use such a way? Because of the page fault. Okay? Why don't you think about it? This is one typical example in the programming to consider. Not many people define the array such a way from the inner group. Right? So why? Think about why. Okay, that is related to the page fault. Then, so first, I think we have a time to discuss about the first in, first out, because it's a simple. Just like the other first in, first out before algorithm is a simple and easy to implement, easy to understand. So we will quickly get the algorithm of the before today. So we have a reference string 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5 means we have the 5 logical memory page. Okay? Which means the program has 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So CPU access first page 4. So this is my program. I'm not sure whether it has a 0. Let's say we have 0, 1, 2, 3, 4, 5. Then CPU first access this one, then next access 2, 3, 4, then next 1, 2, 5. So whenever CPU access this page should be available in the physical memory. So right now we have the 3-page frame. So 3-page frame means we have the 3-page physical memory. So in case one page is 8 byte, physical memory size is 24 byte. Okay, so this is a physical memory. Then first, when 1 is the referred, is there any 1 the first time? Nothing. All 3s are free frame. So this one is page fault. Okay, so let's set page fault as the page fault. This one. Then once the 2 is called, there's no 2. So it's a page fault. So we need to bring the page 2 into the memory. What about 3? 3 is not. So it's a page fault also. Then 4. Is there any 4 over here? No. So we need to decide one of the page frame as the victim page. Our algorithm is first in, first out. Which one is the first in? The first one. 0, 1. In case this is a 0, 1, 2. So page frame number. So frame number 0 is the victim. So replaced by 4. Okay. So it's a page 4. What about the next one? 1 is not.
No.
So we need to find the victim page. So this one is the oldest one, first thing. So this one will be replaced. This page 4. And 2 also, so this one will be replaced. Page 4. 5, there's no 5, so this is oldest one, so goes to here. 5, 1, 2, page 4. And 1, fortunately we have 1. So we don't have to page in again. It's already in the physical memory. So we can reuse. So this is a no page 4. 2 is here. 4, 3. 3, there's still 5, 1, 2. There's no 3. We need to find all this one, that is this. So this is a victim page. So 3 will replace this one. It's a page 4. And the next 4, we need to come in this one. All this one, this, and 5 is here. So how many page 4 in this case? 1, 2, 3, 4, 5, 6, 7, 8, 9 page 4. Many of the students forgot actually the first. This is also page 4. So this is the first in, first out. What if we have the 4-page frame? The same thing. 1, 2, 3, 4 page frame. Okay. Then 1, there images. 2, there images. Then 5 is not, so it's a page 4. Replace all this one. And next 1. No 1, so this one is oldest one. 1, 2, 3, 4. It's a page frame. At page 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 page 4. Which one is better? The more is the better? No. In this case, no. So it depends on what? The pattern of the reference string sometimes. Not always the bigger. Usually bigger is the better, but not always. So you can see if this is a problem in case of the 4, okay? So 1, 2, 5, 1, 2, 3. So if it's rotate R at that time. So what about this one? In this case, usually array, so from the process, it's the heap size. Heap has the, does a heap keep all the array of the data? No, definitely not. How? It has the pointer address. Okay? Address, pointer. Okay, so this one is an outer loop, and this one is an inner loop. So you can think about why this one and this one is different in terms of the performance, specifically the page fault concept. So this one shows the Okay, one more thing. This is the another example of the first in first out for the second reference string. So it shows the 15, 18 code. Okay. So as you have seen before, not always the more page frame is better. This kind of the situation is called related anomaly. This one is happen because of the pattern of the reference of the CPU access as the pages. Okay, so next the class on Thursday we will continue optimal and the other algorithm we will compare and we will talk about the project later. Any question? Okay, so we will see on Thursday. Or we will have a meeting today.